So today I'm going to be talking about the dot product, but in a somewhat more general setting as well. But first, I'll do the familiar dot product, and I'll do it, I'll pick an example. So we have, let's say, the vector 1, 2 dot the vector -1, 1. And so this will be equal to -1 plus 2 equals 1. And so what we did there is first we take the product of the first entry of each vector. So that gives us -1. And then we added the second entry of each vector. That's where we got our 2. And then that was equal to 1. So that's an example of the dot product. And you can do this for more than just two-dimensional vectors. You could do this for n-dimensional vectors. So given vectors a and b, we define the dot product a dot b equals a1 b1 plus dot 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 an bn. So you pair the entries, you add them, and that gives you some number. Another way we could view the dot product is as a matrix multiplication. So dot product as a matrix multiplication. And the idea is that we're going to be taking a row vector, a1 to an, and we multiply it by a column vector, b1 through bn, to produce the same formula we just saw. This is the formula we just saw, and now we're interpreting it as multiplying a vector by a matrix. Now let's look at our previous example and interpret it in this light. 1, 2, -1, 1. And so this is a matrix times a vector, and the dimensions are appropriate, and this is just equal to the same thing we had last time. -1 plus 2 equals 1. And it's easy to see that this generalizes. And so the dot product generalizes. In fact, you could even say a dot b is equal to a transpose b. So you turn first a equals some column vector, and then you just, like for a transpose, you just turn it into a row vector, and then we have a1 to an, a1 to an, and so that's really what the dot product is. It's a relationship between a vector and its transpose. So it's like we view the vector as a matrix. Well, every matrix is a vector, and every vector is a matrix. So what we have here is a vector space V, which is Rn for some, natural number n. That's what we're looking at here, and so that's V, and then we have V transpose, or what I'll call V transpose, which is the set V transpose for V in V. So we have like our small v's and our big v's. These are individual vectors, and this is the set. So and that's the set. This is the set of vectors. That's the set of, so V is n by 1 vectors, or matrices. And V transpose is the set of, one row and column matrices. So this looks more like matrices than those. I mean, you can see that there's a one-to-one correspondence between them. But okay, so here's another way we could view VT, V transpose, of the vector space is the set of linear functions from Rn to R. So recall that M by N matrix, so matrix is linear map we'll call it M for matrix, which takes you from Rn to Rm. Usually these are the same. I mean, often N and M are the same. In this case, they're not. And our matrices, N is just N, and M is equal to 1. So that's from Rn to R, considering the fact that V is a real n-dimensional vector space. And just to remind you, a linear map just means that if you have something like M of RV plus SW, this will be equal to R and V plus SMW, where V and W are vectors, and R and S are scalars, M is the matrix. So that's just what a linear map means. It like preserves the structure of the vector space. It's easy to see that it's a quite obvious fact that V is isomorphic to V transpose. I just commit that to paper, so I mean, you're just taking a vector and flipping it. At least that's the regular perspective you can have on it. And so these two are the same, and this holds in general. So what do we mean by this? So a vector space is over a field of scalars, and so we'll always have, for a vector space V, it'll be equal to some field, to the n. And so we define, here I'm not going to call it V transpose anymore, this is a more standard name, V star, as the set of linear functions. So this is F, but these are functions. F means functions, but I'm looking specifically at the linear ones. From Fn into F. And we have in general, at least for finite vector spaces, which this is because there's an n there, V star isomorphic to V. And one relatively straightforward example is take the vector space of n-dimensional complex numbers. So this is just, let's take arbitrary V in here, then V equals A1 plus V1I AN plus VNI. This is n complex numbers. And so over here, we could define V star equals the set of Hermitian matrices or vectors for V. And this is quite similar to the dot product, but you just conjugate. So we'll say VH equals like V bar transpose, where the bar is conjugation. So if V equals A1 plus B1I to AN plus BNI, then V Hermitian will equal, now it's a row vector, A1 minus B1I, etc. And so this is the transpose, where you also conjugate. And so you can define the dot product again. So if you have two vectors in complex n space, let's call them v and w, for Cn, then you could define v dot w to be h w, which again is just some matrix product, v bar w, and this will be a sum of complex numbers. You know, let's call the v's, instead of writing out a1 plus b1, we could write alpha 1, beta 1, and sort of the using Greek letters reminds us that these are complex values. But there's sort of bars over these. If we're like, if these are the elements of v, then you're looking at the conjugates of them. But you know, each of these is some complex number, and then in general, and then this sum is some complex number. And so this is a function, a linear function, from Cn to C, complex n space to C. And this holds in general for any vector space. You can define this sort of thing from the vector space to its field of scalars. And these are what we call covectors. They're basically 1 by n matrices in some sense. And it's isomorphic to the vector space itself. It could be called the dual space of the vector space. And so at least if we look at those two examples of real and complex covectors, v transpose transpose is equal to v, and v Hermitian Hermitian is equal to v. This case is rather trivial. You're just, you know, taking that thing, turning it into that thing, and then you're turning that back into that thing. And over here, it's, you know, a little bit less trivial. You're taking this and turning it into that with bars over all the elements. But over here, you will double bar them, which is just equal to the regular. You know, the bars sort of cancel. You know, because you're taking a plus bi, you're sending it to a minus bi, and then you're sending that to a minus minus bi. So that's just equal to this. And so this holds in general. So what we want to say is v star star equals v. And here's how you could sort of view it. You take an ordered pair, v star, and this equals f, which is some scalar in your field. So these are vectors, and these are your scalars. And so if you have, you know, sort of just a v, then this is a function which will take a v star input and then give you an f according to some formula. So this is like a function which takes v star, or takes something from the v star space and goes into the scalar field. And this is a function, we have, you know, a v star without a v. And this will be a function which goes from the vector space into the scalar field. And so then this starts to make sense, because if you have v star, then v takes you to f. And so the covector of a covector is a vector again. And I think that sums up covectors.